Hello, I am Nikhil. I am one of the TAs for this course, Physics 241, and I'll be doing the lab recitations for your section of the lab. Okay, so to begin with, for this first week, you have a couple of quizzes. So I'll be explaining the solutions to the second quiz for this week, and this is just for this week. Henceforth, in the future weeks, I believe you'll have to be doing the problems on your own, and I'll still be doing videos, but there won't be solutions to the problems in the quizzes, but there will be other content. So this is just for this week that I'll be doing the solutions to the problems in your quiz. And this is the second quiz, so I'll start off with the first question. The first question of the quiz number 2, asks you what the electric field would be due to 3 point charges that are equal in magnitude and are located at the 3 different vertices, as you can see in this figure. So you have 3 point charges that are located at the different vertices of the equilateral triangle, and the question asks you what the electric field would be, the resultant electric field, due to all of these 3 point charges on the vertices of the equilateral triangle. Where exactly? At the center of the equilateral triangle. So somewhere over here at this point, right in the center of the screen, in the center of the equilateral triangle, the question asks you what the electric field would be. So the electric field due to a point charge, if you look at the field lines would be such that they're radiating out in a spherically symmetric fashion. That is, so from a point charge you have field lines that are going radially outwards. So if you take, for instance, the point charge at the top of this equilateral triangle, at the topmost vertex, the electric field due to that would be in a direction pointing from that point charge to the point which is at the center. So if you draw a line from the position of the charge to the center, that line, or the direction of that line, will give you the direction of the electric field. So it's going to be from this point at the top to the center of the equilateral triangle. That's going in the downward direction, so you have an electric field in the downward direction, and that's the direction of the electric field. But a vector also has a magnitude, so as the electric field is a vector, it'll have a direction and a magnitude. The direction due to the electric field from this point charge at the center will be in the downward direction. But so how do you get the magnitude of the electric field for this particular point charge? The relation for, or the equation for the magnitude of the electric field due to a point charge at a point that is at some distance, say r, from that charge, is the magnitude of the charge times a constant times 1 over the square of the distance, r squared. So it'll be some constant k, the Coulomb's constant k, times the charge q over r squared. So you'll have kq over r squared. That's the magnitude of the charge. Over here it's represented by E3. So it's that's the magnitude, kq over the distance, that is the distance from this charge to the center of the triangle. So kq over r squared is the magnitude, and the direction is downward. So likewise, you can calculate the electric field due to the other point charges that are located at the other vertices of the equilateral triangle. So if I take the point charge at the bottom left vertex over here, then the electric field would be in a direction pointing from that charge to the center of the triangle. So it would be this vector over here pointing in this direction. As I extend this further, that's the vector, electric field vector E1. It'll have this direction, and the magnitude would be given by the same relation, k times q. Since the magnitude is the same and the distance, because of the symmetry of the triangle, will be the same. So the magnitude of this vector E1 will be the same as the magnitude of the vector E3, but the directions are different. Likewise, you can also get the electric field due to the third charge at the bottom right vertex of the triangle. It'll be pointing in this direction and have the same magnitude. So I have these 3 different vectors, all have the same magnitude but different directions. But due to the symmetry of the triangle, if you look at the total angle between these 3 vectors, it's going to be one full circle, that's 360 degrees. And since these vectors are symmetric, located due to the symmetry of this triangle, they will split this full circle into 3 angles that are equal due to the symmetry. So if you divide 360 degrees, which is a full circle, into 3 parts, that's 120 degrees. So the angle between E1 and E2 is 120 degrees. the angle between E2 and E1 is 120 degrees, and the angle between E1 and E3 is 120 degrees. So you have equal angles between these three vectors, and whenever you have n number of vectors that all have the same magnitude, and the angular separation between each of them, if that is same, which is 360 over n, then the resultant of all of those vectors will always add up to 0. So because you have all these three symmetric vectors with equal magnitudes, so their resultant will always be 0. So if I change this equilateral triangle to a smaller or a greater size, such that if I change the length of one of the sides of this triangle, or if I change the area and make it smaller, that will change the magnitudes of these vectors, but since the angular symmetry remains the same, the resultant will always be 0. So your answer, I believe, for this problem will be option number 3. That is, it's always going to be 0. Okay, so moving on to the second problem. In this problem, you have a proton that's located at a distance of 1 meter along the positive x-axis from the origin, and you have an electron that's located at a distance of 1 meter along the negative x-axis. So the question asks you what the resultant electric field would be at the center of this, or at the origin, due to these 2 point charges, the proton and the electron, placed symmetrically about the origin along the x-axis. So if you denote the electric field due to the electron as E subscript E, and the electric field due to the proton as E subscript P, notice that due to the electron, the electric fields, because the electron has a negative charge, its nature is attractive, so all the field lines will be pointing inwards toward the electron. So the electric field due to the electron at the origin will have a vector that's pointing towards the electron, and since the electron is located on the negative x-axis, so you'll have a vector that is located toward the negative x-axis. Okay, so the electric field due to the electron will be pointing towards the negative x-axis. But what about the electric field due to the proton? The proton is located on the positive x-axis, but since proton has a positive charge, the electric field lines will be radiating or emanating outwards. So you'll have a vector. If you want the electric field due to the proton at the origin, so you'll have a vector that is pointing from the proton to the origin. So you go from +1 to 0. So that's also pointing in the negative x-axis. So you have 2 vectors that are both pointing towards the negative x-axis. So you're going to have the superposition of these 2 vectors, or the sum of these 2 vectors at the origin, and since they're both pointing towards the negative x-axis, you just got to add them up. So if you look at the magnitudes of these 2 vectors that are both pointing in the same direction, let's start with the electric field of the electron. The magnitude of that will be k times the charge. Since the electron has a charge that is negative, we have a negative sign here, so it's k times minus of the electron charge E divided by the distance squared, r squared. So I just plug in the values here. The Coulomb constant K is 9 into 10 to the 9 in SI units, Newton meter squared per Coulomb square, and that's multiplied by the electron charge, which is 1.6 times 10 to the minus 19 divided by the distance squared. Since the distance is 1 meter, so that's 1 squared. So if you do the calculation, that comes out to minus 1.44 times 10 to the minus 9 Newton per Coulomb. That's the electric field due to the electron at the origin. And the negative sign here represents a direction that is toward the negative x-axis. You also have the electric field due to the proton. So the electric field due to the proton will have the same magnitude, because the magnitude of the charge is the same, and it's also in the same direction, so it's also having the same value. So you just got to add those 2 values. So if I add those 2 values, 1.44 times 2, that's 2.88, and since both of them are acting in the negative x direction, so my overall resultant, the total electric field due to both of these 2 point charges at the origin, will be pointing towards the negative x-axis. So you have uh, the net resultant electric field, that is 2.88 times 10 to the minus 9 Newton per Coulomb in the negative x-axis. But the problem asks you only the magnitude and not the direction. So I'm just interested in this value, that is the magnitude of the resultant electric field will be 2.88 times 10 to the minus 9 Newton per Coulomb. Alright, so that's two problems. Moving on to the third problem. So in this problem, you have a situation where you've been given an electron that's fired through an electron gun, and it's fired along the positive z direction, and its initial velocity is 20 meters per second, but it's not flying off into free space. It's flying into the positive z-axis, but in a region that has an electric field that's pointing in the negative z direction. So you have an electron that's moving upwards along the positive z direction, but an electric field that's downwards in the negative z direction. But since this is an electron, it has a negative charge, and as an electron has a negative charge, the electric field will apply a force that's in a direction that's the opposite of the electric field. So since the electric field is acting downwards, you'll have a force that's acting upwards. So you have a force on the electron due to the electric field in the upward direction. The Lorentz force due to this electric field on the electron is in the positive z direction. And the initial motion of the electron is also in the positive z direction. So the result will be that because of this electric field and the force acting on the electron due to this electric field, the electron is going to accelerate further and further as it moves through this electric field. So you can calculate the force on the electron due to this electric field using the equation or the relation. The force equals the charge times the electric field. So the charge of the electron is minus E, it's negative, it's minus 1.6 into 10 to the minus 19 coulombs approximately. And you just multiply that with the magnitude of the or the electric field vector. Because the electric field vector is in the negative z direction, I have minus 1.5 Newton per Coulomb in the negative z direction. So if I just multiply the two values, because I have two minus signs, I get a positive sign here. The force due to the electric field on the electron will be 2.4 times 10 to the 19 newtons, but in the positive z direction. So once I have that, once I have the force on the electron due to the electric field, I can then calculate the acceleration of the electron. So using the Newton's second law, force equals mass times acceleration. So the acceleration will just be the force on the electron divided by the mass of the electron. So you can just do the calculation, just plug in the mass of the electron, that's 9.1 times 10 to the minus 31 kilograms. So I'm doing this calculation in SI units. So if you just do the calculation, that works out to 2.6 times 10 to the 11 meters per second square. That's the acceleration of the electron, and it's in the upward direction or the positive z direction. So I have the initial velocity and I have the acceleration. So if you know the initial velocity and you know that the acceleration is this value, 2.6 times 10 to the 11 meters per second square in the positive z direction. So if you have a body that's moving at a constant acceleration, Newton has given us the laws of motion, so you could use those laws of motion and calculate the final velocity of the electron. So I'm going to do that. So the final velocity is the initial velocity added with the acceleration of the electron times t. So you have v equals u plus at, where u is the initial velocity, v is the final velocity, a is the acceleration, and t is the time for which this electron has undergone the acceleration in the region with the uniform electric field. So you've been given this time. This time is given as 0.009 milliseconds. The initial velocity u is given as 20 meters per second in the z direction, and the acceleration of the electron we just calculated is 2.6 times 10 to the 11 in the positive z direction. So you can just plug in the values and do the sum, and that'll give you the final velocity of the electron. So if you just add 20 meters per second times plus 2.6 into 10 to the 11 into 0.009 into 10 to the minus 3 10 to the minus 3 because it's milliseconds, so I'm just converting here from milliseconds to seconds. So I do that conversion over here, and this the product of these two terms, a into t, if I do the calculation, that is 2.37 into 10 to the 6 meters per second in the positive z direction. And I also have the initial velocity, which is in the positive z direction, that's 20 meters per second. So I just add the numbers, 20 plus 2.3 times 10 to the 6. So because this number is much larger than the initial velocity, so the sum of these two numbers will be equal to the bigger number, that's just 2.37 times 10 to the 6 meters per second in the positive z direction. So that's my answer for the third problem. Okay, so that's 3 problems. I'll move on to problem number 4. So it's asking which of the following statements is not true, or in other words, which is false. So I'll go option by option. Let's look at all the options. The first alternative says the electric field lines emanate from positive charges and terminate on negative charges. Yes, the statement is true. So if you have a positive charge, the electric field lines due to that positive charge are emanating in the radial direction outwards because it's repulsive. And for electrons, since it's attractive, it's going to be pointing inwards. So the electric field lines are going to be inwards, and they're going to terminate at the negative charge. So this statement is true. Okay, so going to the next statement. Electric field lines that are spaced relatively far apart imply a relatively weak electric field. This statement is also true. So when you represent the electric field intensity in a region using electric field lines, the more field lines you have passing through a certain cross-sectional area, the more will be the intensity of the electric field in that region. So if your electric field lines are spaced further and further apart and you have fewer field lines passing through the same area, what it means is that the electric field intensity in that region is low. And that's what the statement says. So that's true. So the first two statements are true. I'll go to the next statement, statement number 3. The potential energy of an electric dipole in an electric field can never be zero. Okay, so what is the potential energy of an electric dipole in an electric field? So if you have a dipole, it's just if you have a perfect dipole, you have 2 point charges with opposite charges. So if one of those charges is plus q, so I'll just go to the first figure here, just so I can explain this. So you have 2 charges. I have one charge over here. Let's take this charge q at the left, and I have another charge here. Let's take the other one, but with a negative sign, not a positive. So you have 2 charges that have equal magnitude but opposite signs. So the dipole will be the resultant electric field due to these 2 point charges, and the dipole will be along the direction from the positive charge to the negative charge. So if my negative charge is say on the right, so your electric dipole moment will be pointing toward the right hand side. Alright, so if you place these 2 charges, or this electric dipole, in a region that has uniform electric field, and the electric field is pointing, say, in the downward direction along this direction where the vector E3 points, then the electric dipole, I'm not going to derive this relation, but the electric dipole will have some energy. It depends on how you place this electric dipole in the electric field. So if you just leave these 2 charges, they will align in such a way, they will align with the electric field, because that's a position where this electric dipole will be in equilibrium with this electric field. So because you have a field that's acting in the downward direction, so your electric dipole will align itself in such a way that it's pointing in the direction of the electric field. It will align itself with the electric field. So both these 2 point charges will move in such a way that they'll be along this electric field line. And that's the equilibrium position. So if you try to disturb this system, if you try to perturb it, it will take some energy, and as you do that, that energy will be stored in this electric dipole. And the potential energy that is stored in the electric dipole will be the dot product of the dipole moment, which is along the direction towards the from the positive to the negative charge, and the electric field. So you have the dipole moment vector and you have the electric field vector, and the dot product of those two will give you the potential energy of the system that you need to impart to displace this dipole from its equilibrium position. So as you start displacing it from the vertical position, it will start to gain energy, and the maximum you can displace this system is from the vertically upward position to the vertically downward position. So the maximum energy it will have stored is when it's in the opposite, when it's still aligned with the electric field, but has a opposite direction. And the central value, or the position which I'm showing here in the figure, where your electric field vector or your electric dipole moment vector is directly perpendicular to this electric field, is the position which is right in the middle. So this is where you have imported half of the energy that you need to impart in order to displace this electric dipole from its vertical position to its oppositely aligned position along the electric field. So the amount of energy needed would be the electric dipole moment, that is the charge times the distance between those two charges, that is let's just say that's r. So q times r. The electric dipole moment is q times r times the electric field intensity E times the angle between those two. So that'll be So since this is the dot product, that will be the cosine of the angle between those two. So if it's perpendicular, so cos of 90 degrees is 0. So this the energy stored in the electric dipole moment would be 0 at this position, or you could set it to any value. So the value 0 is just an arbitrary reference value that I'm choosing. I could choose any value that I want. Because it's right in the center, I choose that as my reference, and I set my 0 over there. So I do have a position where my electric dipole moment will have 0 energy. So this statement is not true. I'll come back to the statement. The statement said that the potential energy of the electric dipole in an electric field can never be 0. But I do have a position where it can be 0. So this statement is not true. That's your answer. So the answer to this problem is the third option. Okay, so I already have one of the options which answered the problem, so I won't go through the other two options. I'll leave that exercise to you. You can check that they're true. I won't be doing that here. So moving on to the final question, it's asking whether or not the statement is true or false. So the statement says, there is a point somewhere around a perfect electric dipole where the electric field is 0. That's not true. So if you have an electric dipole, I could just I could just show you the electric field due to a dipole. So here's the geometry due to the electric dipole. So as you can see, you have field lines that emanate from a positive charge. I don't know whether or not this is visible to you, but you have field lines that emanate from the positive charge and go to the negative charge. Nowhere in this diagram do I have a position where there are no electric field lines. The electric field lines permeate the entire space around this electric dipole, so there is no point where your electric field drops to 0. So that statement is false. And I think that answers your final problem. And I guess that's it for this week's recitation. I hope that was helpful. Alright, so see you next week. Thanks for watching.